Okay. Our projector on. We're actually going to start covering section 3.3 because it's a much longer section. So we're going to do all of 3.2, the beginning of 3.3, but the outline for 3.3 is going to be due at the start of next class period. Yep, like I told you guys to do.
The outline of 3.38 or 3.0. That's how that.
All of it, yeah. Because there's no way, I hadn't decided where I was going to stop yet. And
So
so
all 3.3 outline.
all of 3.3 outline is due next year. Yeah. Same day. We're actually doing 3.2. No. Where is that? Let's see. I had printed something out to give to you guys. I left it at home. Yeah, so let's fix this. We're doing 3.2 today. So let's put this on the first page. So 3.2 is Monday. 10, what's today, the 26th? 3.3, this is outlines. This is going to be due Wednesday, 10/28. Then we are going to have a review on November. Yeah, test is through 3.2. Review on Monday, November 2. Yes. Test 2, Wednesday. There we go.
So we're gonna do section 3.4.
Yeah, we will, but that'll be.
The extra day on
Yeah.
30.
And then.
So let's do the class project on the 30th. Everything will be fine. There's only one.
Well, so here's what we're going to be doing. Then we're going to do 3.4 on November 9.
So the class only over 3.2.
Yeah, through 3.2.
That's the test.
Yeah. So then 3.4, then 4.1 on Wednesday, November 11. Then 4.2, Monday, November 16. And then outline 4.3 is going to be the project on Wednesday,
So we
November 18th. Yes. And then Thanksgiving break. Then when we get back on November 30, we will cover 4.3, but there's going to be no outline due because it's already done.
And then we're back on schedule.
Yeah, then we're back on schedule.
But do we have the homework for 4.3?
Yeah, you'll have homework for
That'll be on
4.3.
Wednesday.
Yeah,
The 2nd December.
then 4.4 is on December 2.
That's for the room.
Uh-huh.
4.3 has homeworks A and B and B.
Yeah, I haven't decided. We may actually just stretch 4.3 out and skip 4.4.
Okay, so
Yeah, we may do that. Mhm.
So,
More than likely, that is what I'm going to do.
So there's only one lesson.
let's see the review sheets up at the end of the week.
so the homework will be due November 2nd, well, next Monday for 3.3.
Yeah, so 3.3 homework is going to be due November 2.
Chapter 5, 7, section 3.
Second semester analysis.
Chapter
Chapter 5, 6, and 7.
If you come back second semester, then you can do chapter 5.
Yeah. So I have that printed out. I'll try and remember to bring that print out.
Analysis 2 is in the same book, right?
Mhm.
So if I decide to go ahead and like, you outline for second semester,
Mhm. Nothing's
Way-
stopping you.
Be way ahead of the game.
Yep, you can do that.
You can finish all the outline.
Do it all over
Maybe like
Christmas.
2 or 3 ahead or something.
All the problem with the head.
I don't even know where to end. What section would you end in analysis too? You know?
I have no idea. I haven't made the syllabus up, but I'm thinking that I'm gonna actually cover it all. I think we can get through it all.
Well, you go ahead somewhat, so this towards the end of the semester.
Yeah, I should. Okay, so you guys should recognize this theorem right here. This lemma, let G take D to R be continuous at X naught with G of X naught not equal to 0. Then, oh, I forgot to start the recorder.
Good point.
Yeah, I need to go. Oh no, I've got it going. I have it going. Okay, so then there exists a delta greater than 0 and an alpha greater than 0 such that if X minus X naught less than delta and X is in D, then G of X is greater than or equal to alpha. This is our bounded away from 0 theorem. And we had it for sequences too. If you know that G of X naught is not equal to 0, so let me draw you a little picture. Maybe this is X naught, and maybe G of X naught is this point right here. It's not equal to 0. In my case, I drew it negative. Then, by continuity, I know I have to have a region here where entirely in this region, my G function is non-zero. Okay? It stays in this area here, and it's non-zero. That's our bounded away from 0 function. So, let's see if we can prove it. What's the hypothesis? Let all that stuff. Let G take D.
Assume the hypothesis.
There we go. Be continuous at X naught.
Only Dr. Anderson will let us do that on our homework.
You can copy and paste on your
That's what I
homework.
did, like, I just copied the line.
Yep.
I don't even think Dr. Brown lets us do
Yeah, no.
Well,
that.
you write it by hand.
Well, I mean, when you're typing, you can just copy the line.
Mhm.
It's like, if I can do this in class,
Then you guys can do it.
I tricked him into that one. It's like, so give me this in class.
Well, I still expect to see them typed. Okay, where do we go from here? We've got the hypothesis. Everything after the then is what we're trying to prove, and we only know it's continuous, right? That's if you were trying to show something else was continuous, but if you know it's continuous and you choose epsilon to be a value,
So if you know it's continuous, you should.
yeah, then you choose epsilon to be a particular value. So, yeah, I don't know. I mean, what value do you think? If we're trying to show that G of X is greater than or equal to alpha,
Something greater than 0.
we have to
right?
find an alpha.
We choose that with that.
Or it'd be something greater than 0, right? Since alpha is greater than 0.
Okay, so yeah, let's choose alpha first of all. What do you think we should choose alpha to be? Epsilon is always a positive value. So what did they choose alpha to be in the book? I don't know. Let's get that out. Now, why would they think to do that? That seems to be pretty foolish. I mean, did they
Like
just pull it out of a
epsilon
hat?
over two.
It's like an epsilon over 2. They're taking half the distance from G of X naught to 0 because they know that that's going to be a non-zero value. G of X naught is non-zero. This is a non-zero value, so they just chose it. Now, what do you know? Apply your delta for this alpha. By continuity, I know that there exists a delta greater than 0 such that, what's the definition of continuity?
That X minus X 0.
For all x in D with Oh, I ran into my 2. Let's move that down a little bit. For all x and d, with x minus x naught less than delta, we have g of x minus, gotta let the computer catch up, there we go, x naught. I'm just using alpha equal to epsilon and let's see what happens.
So the alpha is basically epsilon. So
Yeah, at the moment.
I didn't know you could do
I could. Yeah. Now, we're trying to get a g of x. So what is g of x equal to? Because we're trying to get this value right here, g of x in absolute value all by itself. Can I start with, let me show you this right here. G of x naught is equal to g of x naught minus g of x and plus g of x.
And then,
Triangle inequality, right? I wanted a g of x naught minus a g of x. I broke it at the wrong spot. So then solve that for g of x. That is going to be greater than or equal to g of x naught minus g of x naught minus g of x. Are we good with
They
that?
just did that in the book.
They did.
No one's. On the house, so.
Every book's going to do it. It's not just this book. Every book does it.
How do they expect? Dr. Anderson, maybe you should just write a book.
You're supposed to have a teacher.
But there are people that buy these books and
They figure it out.
They just.
Hours and hours.
Dr.
Mhm.
Anderson, maybe you should just write the book for this class.
Can I actually make self-teaching analysis?
I see some prove that
There are books that people claim you can learn analysis from all on your own, but I haven't found one that worked real well. There's something to be said about someone explaining it the first time you see it.
I find that hard to believe that this book self-teacher stuff.
Okay, now we wanted to switch the order of these. Can I do that?
yeah, money.
Yes, you can. So that's g of x naught minus g of x minus g of x naught. Now, what do I know g of x minus g of x naught right here?
It's less than alpha.
So if it was negative, it would be
Greater than?
greater than alpha. Greater than a minus alpha, right? Well, what was g of x naught equal to? And what is alpha equal to?
Yeah, that's how many is there.
Yeah. So what is that actually equal to? Yeah. Which is our alpha. So you started over here with this g of x, and you got bigger than alpha.
So you said that it was greater than g of x naught minus alpha because of the order that it was written.
Say that again?
When you put the greater than g of x up.
Mm-hmm. Yeah, because I have this inequality right here. And if that one wasn't sufficient, I have that one right there. And they have to all go the same direction. I can't have them flipping direction on me.
Well, I guess my question more is if it said like, g of x minus g of x naught would still be greater than.
Oh, you're talking about this right here?
Yeah.
You can switch the order inside absolute value
But it'll
Because-
still be greater than?
because the absolute value doesn't change. It's always a positive answer. If you think about it, what is 1 minus 2 in absolute value? Is that the same thing as 2 minus 1?
Yeah.
The absolute value takes care of changing the order on it.
But we'll explain that to the office.
Yeah, that takes a lot more time. Any other questions on that? Okay, so that was the lemma. Why did they take the time to prove that lemma?
It's important.
Yeah, it's important for the theorem, the algebra theorem.
Third,
Yeah, the division one. So here's our algebra theorem. Suppose f takes d to r, g takes c to r are continuous at x naught and d. Then f plus g is continuous at x naught, f times g is continuous at x naught, and if g of x naught is not equal to 0, then f divided by g is continuous at x naught. So we've had these for limits. Now we're going to prove them for continuous. We can do the same old epsilon delta proof form, or you can do limits. Which one do you want to see? The book did limits, but you can do either one, epsilon or delta or limits. Let's do epsilon delta, because you have the limits in the book. So
this one's easier.
they're
The
both
first one.
equally easy, I think. I'm going to actually start the proof right here, so I don't have to go scrolling too far down. Yeah.
For all three.
This is going to be, I'm going to put them all in there, but let me put the hypothesis down.
Is this the same thing that like you prove 1 is equal to 3 and 3 is equal to
No,
2?
No.
No, these are actually equations.
These are the limits that if you have equations that are, that have limits, then they're addition and multiplication.
Unfortunately, you can do, one implies the other.
Yeah. So we're going to look at f plus g. Then I know since f is continuous, there exists a delta 1 greater than 0, such that for all x and d with x minus x naught less than delta 1, we have f of x minus f of x naught is less, and I'm betting we'll need an epsilon over 2. And there exists a delta 2 greater than 0, such that for all x and d, and this is just an application of the definition of continuous. What should we let delta be equal to then for this one? Minimum. Then for all x and d with x minus x naught less than delta, we have f of x plus or minus g of x minus f of x naught plus or minus g of x naught. I need that parentheses and then close it. Go ahead and group them together. This becomes f of x minus f of x naught. I'll make these not absolute values, not skip the steps. Plus or minus g of x minus g of x naught. Apply your triangle inequality. What is that? How come that isn't plus or minus, by the way?
Because it will be the same in absolute value.
Yeah. Well, when you apply the triangle inequality, a minus goes to a plus and a plus goes to a plus. So this is by triangle inequality. But each of these is less than epsilon over 2. So, yep. Thus, f plus or minus g is continuous at x naught. So that's 1 is proved. I'm using the same epsilon. Now let's go ahead and prove 2. It's going to be multiplication. What is the arithmetic for the multiplication? Let's go ahead and write it out. Let me leave a little bit of room. And so for all x and d with x minus x naught less than delta, we have f times g of x minus f times g of x naught. What is that going to be equal to? We have to add and subtract something, right? F of x, g of x minus f of x, g of x naught plus f of x, g of x naught minus f of x naught, g of x naught. Right? Adding and subtracting 0. Apply your triangle inequality and factor out an f of x. And you get a g of x minus g of x naught plus, I'll sneak it, well, I'll put it down here, plus what gets factored out from the second? G of x naught. Then you have f of x minus f of x naught. Now, we're going to have each of these be less than epsilon over 2 times something. So we have to have some bounds. How do we get some bounds? The second one, I can bound by g of x naught plus 1, a positive value, right? And the first one, we have to do some algebra on, right? Yes. So let's do the f of x naught one. I know there exists a delta 1 greater than 0, such that for all x in d with x minus x naught less than delta 1, we have f of x minus f of x naught is less than epsilon over 2. And then I'm going to put this g of x naught plus 1. G of x naught absolute value plus 1. So that I don't have division by 0. But if that's the case, then I can find a bound for f of x, right? Okay, so what I'm going to do is I'm going to go up here and choose my epsilon to be less than 1. I can do that because as soon as I choose epsilon less than 1, then right here I can say that I'm going to have f of x minus f of x naught is less than 1 over 2 g of x naught plus 1, which is some constant. So we'll just call that equal to, what do you want to call that constant? A? Okay. Then I'm going to have minus k is less than f of x minus f of x naught is less than k, which tells you that the absolute value of f of x has to be less than the absolute value of k plus, let's see if I can do this. Oh, it's not going to fit right there. Let me move it down. Okay, if k was negative, which it isn't, it's a positive value, so I guess I don't need to worry about the absolute value of k. I can just do k plus absolute value of f of x naught. That's going to be the biggest upper bound we're going to have. So I can come down here and write this less than or equal to f of x now becomes k plus absolute value f of x naught times g of x minus g of x naught plus g of x naught times f of x minus f of x naught. Now, we just have to take care of the g of x. And we want g of x minus g of x naught to be less than what? We wrote it down. Where's g of x? It's going to be k plus, so it's epsilon over 2 k plus the absolute value of x, f of x naught. Oh, no one's going to be able to read that. Let's move that. 2 times k plus f of x naught. So I ran out of room, but that's what that is. So then bring this down here, and what should we make delta be equal to? It's a minimum of delta 1 and delta 2, right? And so then we can finish our computations. The first one's going to be k plus absolute value f of x naught times epsilon over 2 times k plus absolute value of f of x naught. And then the second one becomes g of x naught in absolute value times f of x minus f of x naught over, and then, oh, that part became replaced. Sorry, I forgot this. Epsilon over 2, wake up computer, 2 g of x naught plus 1. But that's going to cancel and give you epsilon over 2, and those are going to be less than 1. So that becomes less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. Thus f times g is continuous. At x naught. The division one we've done when in the notes. It's just like the limit one. The only difference is you don't have the 0 less than the absolute value x minus x naught. So I'm going to let you go ahead and mimic this on your own. Mimic the limit one. This exact mimic, and it's also the same as a proof in the book. They do an epsilon delta proof for this one. Okay, so let's look at theorem 3. Theorem 3 is now talking about function composition. This one's a really easy theorem. It's shown up on many a test. I would know this one.
So you're hinting.
I am hinting. I haven't written the test yet, so it's a hint.
I bet it probably will be on that.
Well, that's probably a good bet. I like it.
If it's not that great, I'm be disappointed.
Sorry. I don't mean to make you disappointed. We just hope I remember all these promises of mine. There we go. Let f take d to r. And g take, this is not the derivative of d, it's just some other set, d prime to r, with the image of f a subset of d prime.
It's not prime, no,
We call it prime, it's just another set.
it's not.
It's not a derivative, yeah. Mhm.
How would you do it? I'm like, was that like derivative?
Nope, it's just another set. Assume f is continuous at x naught in D and g is continuous at f of x naught. And f of x naught then is going to be in D prime because the image of f is contained in D.
Okay, I have a question.
What's your question?
To verify, D prime is the derivative of D, right?
D prime is not a derivative.
That's just.
Yeah, this is just another set. It's confusing everybody. D prime goes away. We'll call it C. C
I
with,
just don't get why they do that. Like, why they do-
because they're trying to make the beginning sets look the same. The image of f is a subset of C. Yep, that's all it's saying.
I'm not an expert with X.
And f of x naught then is this element of C.
I gotta understand.
Okay, yeah, they're just trying to make you think that the domains are going to be somehow related. And it's not the domains, it's the range of one is in the domain of the next. Yeah. Now, what we're trying to do is show that G composed of F is continuous at X naught. So that means we need to fix an epsilon, right? As always. What is G composed of F? What is that equal to? G of F of X, right? So what we need to do is, if I'm looking at where G composed of F is continuous, I need to know that G is continuous at that point. Okay? Since they told us that G was continuous at F of X naught, I know there exists a delta greater than 0 such that for all y in C with y minus f of x naught less than delta, we have g of y minus g of f of x naught is less than epsilon. Now, look, I have these y's minus f of x naughts are less than delta. So let's apply that. Since f is continuous at x naught, I know that there exists a delta 1 greater than 0, such that for all x in D with x minus x0 less than delta 1, we have f of x minus f of x0 is less than delta. Notice I made it less than that delta right here.
So,
Almost. And so for all x in D, with x minus x naught less than delta 1, we have G composed of f of x minus G composed of f of x naught is equal to G of f of x minus G of f of x naught. Well, these f of x's are behaving like this y right here. And so then if I plug it in, I have a g of y minus g of f of x naught. I can conclude that that's smaller than epsilon because these guys are smaller than that delta. Does that make sense? So that has to be less than epsilon. And I'll put the less than epsilon up here. It's less than epsilon since f of x minus f of x naught is less than delta. What's the conclusion? Thus, G composed of F. Yeah. Two applications of continuous gets you that. a nice little theorem. Any questions on that? Oh, it is a short proof. It's a wonderful one. This one is a problem that we're going to need later in life. So we're doing it now. Later in life. Later in,
How much later in life?
sometime between now and December 16.
Particular derivatives?
No, it could be continuity.
Not sometime when you take the PhD class.
I just had it marked that I needed to do it. I don't remember why. I just have it marked that I need to do this one. So let P and Q be polynomials and X naught be a zero of Q of multiplicity M. Prove that P over Q can be assigned a value at X naught such that the function thus defined will be contiguous there if and only if X naught is a zero P of multiplicity greater than or equal to M. Yeah, you had a problem sort of similar to this. So, oh yes, we do zeros in precalculus. Let P of X, Q of X be polynomials. And X naught be a zero of Q of multiplicity M. Then, by definition, I know that Q of X is equal to X minus X naught to the M times some R, I'm going to call it R1 of X, where R1 of X naught is not equal to 0. So you can factor out your 0, right? Now this is an if and only if proof. Yeah, we have to do them both ways. So which way did we want to look at first? Bottom one first? Okay. So backwards first. No, it doesn't matter. Let X naught be a zero of P of multiplicity N greater than or equal to M. Then how do I write what P of X is equal to? X minus X naught to what power? N. I'm going to write it as an R2 of X, where R2 of X naught is not equal to 0. Now I have to look at P over Q and figure out what value to assign it so that it would be continuous. Let's look at let's do some basic arithmetic first of all. Well, pre-calculus. P of X over Q of X is going to be X minus X naught to the P is N, Q is M, and then R2, wait, which one is? Q is on the denominator, so it's R2 of X divided by R1 of X. I know R2 and R1 are non-zero at X naught. So we just have to figure out how to define this. I know N is greater than or equal to M. So what is is N minus M positive or negative? Yeah. Since N is greater than or equal to M, N minus M is greater than or equal to 0. Thus, P of X naught over Q of X naught is equal to, well, let's just define it and I'll show you what's happening on it. So we're going to make it be this function. It's going to be X minus X naught to the N minus M R2 of X over R1 of X. In the case that x is not equal to x naught. If x is equal to x naught and n is bigger than or equal to m, what would that be then? Yeah. So is that function going to be continuous? That's the only thing we have to do. Yeah. Let xn converge to x naught, where xn is a sequence in R. And I want it to be different from x naught. Then what is the limit as n goes to infinity f of xn? So limit is n, oh, I need different, I got an n already. Let's take a w, and these are going to be w's.
Never use that.
Yeah, w's are going to be,
Not so good.
yeah, I know, but we already had an n used up there. F of xw is going to be xw minus x naught to the n minus m, r2 of xw, r1 of xw. So what happens to this first part inside that exponent? Becomes 0, right? Yes. 0 to the n minus m times r2 of xw. Oh, I need a limit of that. When I take the limit of that, I get r2 of x0 over r1 of x0. But both of those are non-zero, so all of that is going to be equal to 0, which is which is p over q of x0. Thus, p over q is continuous at x0. Okay, those are going backwards. Yeah, and the forward says, assume p over q of x can be defined at x0 such that the limit as x goes to x0, p of x over q of x is equal to p of x0 over q of x0. That's what it means to be continuous. Well, what is p of x0 over q of x0? P of x0 was x minus x0 to the n, r2 of x0. Q of x0 was x minus x0 to the m, r1 of x0. Well, that's x minus x0 to the n minus m, r2 of x0 over r1 of x0, where r1 of x0 is not equal to 0, r2 of x0 is not equal to 0. So this is defined at x0. Let's see. I'm going to put a now right here. That is going to be well defined at x0 for what? Well defined means that you can evaluate it. You need n minus m greater than or equal to 0. If n minus m is negative, then you have division by 0. Yep. Thus, I need n greater than or equal to m, and hence the multiplicity.
That should be for if n minus n equals 0.
What?
That one.
This one?
No, that one for if n minus n less than 0. That should be less than 0 or
Yeah. No, less than, because I'm negating this right here.
Oh.
Yeah, so it's strictly less than. So, and hence x naught is a multiplicity of q of 0 for q. Which is greater than the multiplicity of 0 for p. Greater than or equal to, which is what we wanted to show. Yeah. Yay. So that one's just writing it out as a polynomial equation. We're going to come back and reference that. So don't forget that we did it, but it's not going to show up on the test. Yay. 3.3, there are 4 things. Uniform continuity is the big one. And in uniform continuity, you're talking about open, closed, and compact sets. Compact sets are going to be sets that we're going to find out are closed and bounded. Open sets are not exactly the opposite of closed sets. You can have sets that are neither open nor closed. So they're not exactly opposites, and we're going to get to that. But what we're looking at today is uniform continuity. Uniform, whenever you see the term uniform in mathematics, that means epsilon depends on delta only. Uniform means epsilon depends on delta only. It cannot depend on x. That's what uniform means. So if I'm talking about uniformly differentiable, that means the epsilon for differentiability depends only on delta, how close you are, but not on the particular value you're differentiating at. So let's look at a definition here. A function f takes d to r is uniformly continuous on E if and only if for every epsilon there exists a delta such that if x minus y is in E, x minus y is less than delta, then f of x minus f of y is less than epsilon. What's the difference between that and just continuous?
It's kind of like the Cauchy version of
It is very much like the Cauchy. You would have an f of x naught there, and this would be an x naught right there. In other words, you're fixing the point. Uniform continuity says it works no matter where you are. It works everywhere you are. That's what you're trying to do. Now, the negation of this definition above, it says it's not uniformly continuous if and only if there exists an epsilon instead of for every epsilon. There exists an epsilon such that for all delta, there exists x and y in E with x minus y less than delta and f of x minus f of y greater than or equal to epsilon. So those are our 2 definitions. Let's show, first of all, uniformly continuous. You actually have a homework problem doing this. Show that the function f of x equal 1 over x is uniformly continuous on the interval 1/2 to 10. So let f take the interval 1/2 to 10 be defined by f of x equals to 1 over x. Fix epsilon greater than 0. And our whole goal is to find deltas so that delta, not epsilon depends on x. This should be delta depends on x only. I got this backwards. I'm thinking 2 dimensions. Okay. Fix epsilon. Let delta greater than 0 such that delta is going to be equal something. Then for all, now we're gonna have x and y in 1/2 to 10 with x minus y is less than delta. We have, now let's do our algebra. F of x minus f of y. What is f of x equal to? 1 over x minus 1 over y. Common denominator, what does that look like? Over x times y. Notice I'm not going to have division by 0 happening because the interval doesn't contain a 0 in it.
So it's fine.
Yeah, xy is not going to be 0. What is the smallest value x times y can be if it's on this interval 1/2 to 10? Yeah, 1/4 times 1/4. Sorry, 1/2 times 1/2, you get 1/4. So that's x minus y over 1/4. Yeah, so each one, put the smallest value in for each of them. So that becomes a 4 times x minus y. Well, x minus y is delta, so we're going to have a 4 delta. So we want that to be equal to epsilon. What should we make delta be equal to? Are there any x values in that definition of delta? X minus y is down here, but in this definition up here, there's only epsilon, right? So thus f is uniformly continuous.
So
Mm-hmm.
the only difference is that when we say the delta equals something,
Yeah.
something delta, I mean something else. No, it's
Yep. Mm-hmm.
awesome now.
Well, you know, that's the first example.
I guess they get harder.
I have another one. You'll notice something about them. They all have an interval that has an upper and a lower bound to it. Okay, so let's let f take minus 4 to 4 to r be defined by is equal to x squared. Fix epsilon greater than 0. As always, let delta greater than 0 such that delta is going to be equal to something. Then for all x and y in the interval minus 4 to 4, with, I always forget this part, with x minus y less than delta, we have f of x minus f of y. Well, what is f of x equal to? And what is f of y equal to? When you see x squared minus y squared, you really feel like doing what? Factoring, right? Yeah, or circle, but we're going to factor. So that would be x minus y times x plus y.
Yes.
Well, x minus y is less than delta. What is an upper bound for x plus y if you know that both x and y live in 4 to 4? 8. So we want 8 delta to be less than epsilon. What should we choose delta to be equal to? Mhm. Is it uniformly continuous?
Yes.
Yes. Since delta depends on epsilon only, f is uniformly continuous on the interval minus 4 to 4. Take my box away. There we go. Let's do another one. Not uniformly continuous. Now it's changed. Bless you. Why? It's an unbounded interval for one thing, right? Yeah, unbounded interval, when you don't have a linear function, you usually aren't going to get uniformly continuous if you have an unbounded interval. You need a bounded interval. So let f take minus infinity to infinity to the reals be defined by f of x is equal to x squared. Fix epsilon greater than 0. On the negation of it, we actually get to choose the epsilon that we want. I think epsilon equal to 1 is going to work. I was just thinking about it. Yeah.
You could just choose something really big. Right?
Yeah, because you're going to let the deltas go to 0. And it's going to break it. So choose epsilon equal to 1. Let delta be greater than 0. Then let y be equal to, and I'm going to choose these to be strange. I'm going to choose y to be, notice what's happening. If you think about your x squared function, it's getting steeper and steeper and steeper. So if we want some place where really close together, they have a difference of 1, that means that we're going to want our x and our y to be, if I make y to be delta, I'm going to make it 1 over delta. That'll make it big. 1 over delta, and x is going to be y plus delta. Now then, x minus y is going to be what?
Y plus delta minus
Yeah, it's going to be y plus delta minus 1 over delta. But what is y equal to? 1 over delta plus delta minus 1 over delta. Yeah, which is equal to delta. So x minus y is equal to delta. Maybe I'll make that a delta over 2. And tell me about f of x minus f of y. Yeah. So y plus delta squared minus 1 over delta squared. But y is 1 over delta. Oh, I made this a delta over 2. I keep forgetting. Well, FOIL that out. What do you get? 1 over delta squared plus, the deltas are going to cancel. You have 2 times 1/2 plus a delta squared over 4 minus 1 over delta squared. 1 over delta squareds are going to cancel, and that becomes delta squared over 4 plus 1. Well, that's certainly bigger than epsilon. Epsilon we chose to be 1. So this is not uniformly continuous. Yeah, it's not smaller than epsilon. Now, suppose you thought this was going to be uniformly continuous. Let me show you the incorrect proof. Because you're going to run into this, so you need to know what it's going to look like. You're going to let f take the reals to the reals be given by f of x equals to x squared. Let delta greater than 0 such that delta is equal to something. Then for all x, y in the reals, with x minus y less than delta, you're going to have f of x minus f of y. That's equal to x squared minus y squared. X minus y, x plus y. What is your, that's less than delta times, what's your bound for x plus y? Infinity. No matter how small you choose delta, you can't overcome that infinity. That's the problem. As soon as you come into this problem right here, you know it's not uniformly continuous. I can't spell.
You can't prove it.
Yeah. That bound goes to infinity, so that doesn't work. Okay, we have one more to show not uniformly continuous on. Yeah, we saw an example of that earlier, but I had it going from 1/2 to 10, which was a bounded interval. 0 to 1 is also a bounded interval, but what's the problem with 1 over x at 0? Undefined, yeah.
Wait for that. Zero.
Mm-hmm. So we know, we suspect that it's going to not be uniformly continuous because it grows very rapidly. Uniform continuity means slow growth, slow equal growth. So like straight lines, uniformly continuous. Exponential, not a chance. Hyperbolas, not a chance. And 1 over x is a hyperbola. So we're going to choose, what do we want to choose epsilon to be equal to on this one?
One again?
Okay, choose epsilon equal to 1. Let delta be greater than 0 be any value. We have to choose x and y to be certain values. Let me see what I chose so I don't have to refigure this one out. It's going to be, I chose delta to be smaller than 2. Let delta be greater than 0. Delta is going to 0. So I'm going to choose delta to be less than 2. Let x be delta over 3. And y be delta over 6. Then tell me about x minus y.
Delta.
What does that say to you? Is it let delta be greater than 0? Is it delta
Is less than 2. Remember, deltas are going to 0. We're letting delta get smaller and smaller and smaller. So I'm just starting it smaller than 2 rather than,
Oh, okay, okay.
Yeah. so
I'm gonna just say let 0 be less than 1.
yeah, I could. Mhm.
Um,
Yeah, so it's 6 delta minus 3, 2 delta minus delta. Well, that's definitely less than delta, right? Mm-hmm. Now tell me about f of x minus f of y.
1 over x.
Yeah, let me plug in for what x is. First of all, x is delta over 3, delta over 6, yeah, 3 over delta. What is 3 minus 6? But delta is smaller than 2, so this value right here, the biggest, the smallest this value can be, it'll be 3/2. Yeah, it's bigger than 1. Mm-hmm. you have a couple of homework problems, let me know. Let's see. We are done for today.
Let X and Y.
When you're showing the negation of uniformly continuous, it says there exists an epsilon so that for all delta, there exists an x and a y. So you get to choose epsilon, you get to choose x and y. X and y have to be dependent on delta so that f of x minus f of y is bigger than epsilon. So the things you get to choose are, you get to choose the epsilon, and then you choose the x and y based on delta. They have to be functions of delta. Yeah. Okay, we are done for today. We will start here next time. So 3.3 will look a little bit familiar when you start next time. Do what? Yeah, outline for 3.3 is due next time. Mhm.
So is it just lot 4?
Yeah, I have to make one for it. I forgot to make one for it.
I have more.
Okay. Let me stop this recorder first of all.